Hello, everyone. My name is Ding. I'm a PhD candidate at George Mason University. Our work is networked beamforming in dense millimeter wave WLAN. It is a joint work with Pania, Dr. Pars Patek, and Dr. Zijian. Okay, nowadays, wireless traffic is increasing in a tremendous way. And the millimeter wave frequency and the spectrum is used both for the wireless local area networks and the 5G NR cellular networks to provide gigabits per second data rate for users. In millimeter wave WLAN, the standards such as 802.11ad and 802.11ay leverage the 60 gigahertz frequency with more than 2 gigahertz bandwidth to provide high capacity and scalability for new applications. For example, the applications like the bandwidth-hungry AR, VR applications could be support for multiple users in millimeter wave WLAN. And people can enjoy high-resolution volumetric video streaming with low latency. Additionally, tons of IoT devices could communicate and cooperate in a fast manner, for example, in the smart factory. However, moving to the higher frequency will cause high attenuation of the signal. To compensate for the high attenuation of the signal, we use the phase antenna array to form the signal as a beam to point to the specific direction of the user, which is called beamforming. But the biggest challenge of using beamforming is to select the best beam. We have to search many possible candidate directions, which will lead to a large overhead. Additionally, more and more APs are deployed in millimeter wave WLAN, not only to provide large coverage, but also to provide high spatial reuse or provide reliability to human blockages. For example, in recent works, dense AP deployment is used to combat self-blockage, to provide seamless coverage for users, or to provide spatial reuse or even localization service. Additionally, we also observed the same trend of decentralization in the 5G NR cellular networks. Okay, so this dense AP deployment can bring us this benefit. It also increases additional beamforming overhead. Okay, now let's take a detailed look at the beamforming overhead in the 802.11ad and the AY millimeter wave WLAN. Okay, this is a typical 802.11ay beacon frame. And for the AP beamforming process, so each beacon will use different TX sectors to send to the different direction. And also, if we want to train the RX set, we need to add the training frame of like the different RX beams at the end of each TX beacon frame. In that case, the beamforming transmission time equals the time to transmit a beacon frame times the plus the total time of training all the RX beams plus the time to the interframe spacing, and then times the total number of the TX beams. For instance, typically with like 64 TX beams and 16 RX beams, it takes around 5 milliseconds for just one AP to do the beamforming. And another thing is that to support spatial reuse and this reliability, multiple users have to be in the same collision domain. So they have to do the beamforming in a sequential manner, one by one. So in a dense network of the 10 APs, they are in the same collision domain. So 50 out of 100 milliseconds of one beacon interval will be just used for the beamforming. Okay, to reduce this significant beamforming overhead problem in millimeter wave WLAN, there are some great solutions proposed. So these solutions focus on reducing the beamforming in the link level. So they are focusing on reduce the number of the beams searched per AP. So these solutions include using the compressive sensing or multi-armed beams or reconstructing the underlying path with CIR or the PDP. But the total overhead still increased with the number of the APs. So to compensate for this link level beamforming solution, we are thinking of reducing the number of the APs to reduce the beamforming overhead. So we ask this question: can we just use a subset of the APs to do the beamforming, but still to keep the beams updated? And we call this solution networked beamforming. So to select which AP to do the beamforming is not an easy problem. So we want to first investigate and find whether there are some underlying patterns we can use to help us to select AP. So we conducted a measurement study in the typical dense mmWave WLAN. Here, we deployed 8 APs in a university atrium, and we also used the Acre laptop as the client and asked this client to move in different routes in this room. And also we modified the driver and extract the beam index and the per beam SNR at the client side. And here we show like the best sector selected by the client and also the SNR change at each step when the client is moved. And here we have 2 observations. The first observation is that actually the best sector selected by the client does not change all the time. In that case, not all APs need to do the beamforming in every beacon interval due to this beam coherence. What we need to do is just ask the AP with a high SNR change to do the beamforming. But the problem is that without doing the beamforming, how can we know the SNR change? So to answer this question, we have the second observation here. We also found actually the different APs have correlations between their SNR change. In that case, we can use one AP's SNR change to predict another AP's SNR change. And if this change is significant, we can ask this AP to do the beamforming. And these observations form the basis of our network beamforming scheme. Okay, in this project, we proposed a network beamforming scheme to select a subset of the APs to reduce the beamforming overhead. And we solved 2 important challenges. The first challenge is how to select a subset of the AP. And we defined a concept of uncertainty as the probability of the significant SNR change. And then we can just select the APs with high uncertainty to do the beamforming. And the second challenge is how to capture the correlation between AP's SNR change. And we built an uncertainty prediction model based on a wall walking process. And furthermore, to investigate our scheme, we built a test bed based on the commercial devices. Okay, this is the procedure of our beamforming AP selection process. As a first step, we will do a wall walking process to collect the channel data. And then for each input and output AP pair, we calculate the beamforming SNR change, clustering them and calculate the uncertainty for each cluster. And then during the runtime, given the observed beamforming information change for the input AP, we can use our model to select the APs with high uncertainty to do the beamforming. Okay, now let's give you a toy example to show how we built our uncertainty prediction model. Based on the wall walking data, we first define the input and output AP pair. And then we calculate the SNR different matrix between time t and time t prime. Here, the SNR matrix just represents all the SNR values for the different Tx and Rx sector. And then for the input AP, we reduce the matrix to a vector by selecting the Rx with the highest SNR, and we reduce the output AP matrix to a scalar by summing up all the dimensions. Then we put the input vector and the output scalar in a tuple. In the next step, actually we cluster this similar input AP vector in a set using Euclidean distance. And lastly, we count the percentage of the output SNR delta, which is higher than the significant SNR change threshold in the cluster. And then we use this probability to represent the uncertainty of that cluster. And the intuition here is that if we observe the more significant SNR change instance for that input vector, the higher uncertainty of that vector, of that cluster. And then during the runtime, for each input AP prime, we first reduce it to the vector D. And then we compare this vector for all the centroid of the clusters in our model. And then we find the closest cluster and use that cluster as uncertainty P as the uncertainty of this output A. Take a simple example here. What our model can do is that now if we observed the beamforming information change for APA and use our model, we can predict whether APE needs to do the beamforming for the next beacon interval or not. Okay, in terms of the test bed, here we deployed 8 air-fed 60 gigahertz APs, each one with 8 antenna patches, and we use the Acre laptop also equipped it with the 802.11ad chipset, and the laptop just have 1 antenna patch. And here we do 2 implementation efforts. The first one is we modify the driver on the client side to extract the per beam SNR and the beam index. And the second modification is that we modify the firmware of the AP to customize our codebook on the AP side. And then during the walking process, we collect the beamforming information of more than 250 steps in the atrium to build our prediction model. Lastly, we compare the different AP selection schemes to show the feasibility of our network beamforming scheme. Firstly, we want to investigate how well our uncertainty prediction model can capture this beamforming information change. So this figure shows actually the estimated uncertainty collected from all the experimental data, and we compare it with the ground truth normalized beamforming information change. So here we can see that our uncertainty prediction model can capture the beamforming information change effectively. Okay, next we conduct another experiment by asking a client to move in the room and perform different AP selection scheme. The first one is the fixed AP, the fixed one AP, which means in the situation, just one AP conducts the beamforming, and that client just connects with that AP. And all AP means we enable all the APs in the network to do the beamforming, and the client will select the AP with the highest SNR. And we also use the Oracle BF as the upper bound by assuming that actually for the client at each step, it's known the best SNR provided by which AP in advance, and just that AP do the beamforming. In contrast, our network beamforming scheme used our uncertainty prediction model I described before to select a subset of AP to do the beamforming. Okay, and actually our preliminary results show that our network beamforming scheme can reduce the number of the APs to do the beamforming in each beacon interval, which results in lower beamforming overhead and higher throughput. Okay, in conclusion, we proposed a network beamforming scheme based on an uncertainty prediction model, which can reduce the beamforming overhead from the network level and improve the network throughput. And of course, there are some limitations and the challenges we are working on. The first one is fine-tuning the prediction model. So far, we are empirically select some parameters like the clustering distance or the threshold so far. So we are investigating how, the different parameters will affect the performance of our system. And also we are trying to modify this offline version to an online version of the prediction model. In that case, the client which use our model also contributes its beamforming information to the model to refine the model. And secondly, we are also trying to combine this link level, our network beamforming scheme with the existing link level beamforming schemes to further reduce the network beamforming overhead. And lastly, we want to investigate how this limited beamforming information will affect the following resource allocation. And this will be our future works. And this comes to the end of my presentation. Thank you and welcome any questions.